Sources of magnetic field summary. We will start with the Savart Law. That gives the magnitude and the direction of the magnetic field surrounding a current-carrying wire. So we start with the differential form. This ds is a wire segment in the direction of the current, a real tiny wire segment, that's why it's a differential. R hat is the unit vector that points from the wire segment to the point where you would like to find the magnetic field. And then r squared in the bottom, that's the distance from the wire segment to the point. Here's a wire down here. dB is a magnetic field due to the wire segment ds, and ds is right over here, and is pointed out of the page. You can either do that by evaluating the cross product or using the right-hand grip rule. The total magnetic field due to the entire wire here at point P is found by integration. And here's the Biot-Savart law, where we're integrating all the little pieces of ds along the wire and all their contributions to the magnetic field at point P. Ampere's law is another way of evaluating the magnetic field. It's simpler, and it also requires a high level of symmetry. So we will choose a symmetric path, shown here in the dashed line, called an Amperian loop. And you need B to be constant on that path, and it certainly is. And it has to be parallel to ds, the line segment, so the dot product reduces to bds. I is the current passing through a surface, so I would be here, for example. Could be either coming out of the page or into the page, and it is enclosed by the chosen loop. The Amperian loop below is indicated by a dashed line encircling a current-carrying wire coming out of the page. That's this guy right here. We will be using a line integral in evaluating this. This just means we sum up all the little pieces of ds along whatever line we've chosen. When you do that, that will equal mu0 times the current enclosed by your curve. So in this case, we're integrating along this path, so that's just the circumference of the circle. That will add up the values of b dot ds at every point on the curve. If there is more than one current enclosed by the loop, then the current directions have to be taken into account. We will assign a positive value to a current into the page. That's shown right over here. There's one current carrying wire. And a negative value to a current out of the page. So we have two currents there, each of magnitude I, one into the page, one out of the page. Their sum will be 0, so the total enclosed current in that case is 0. We have some important configurations that should, if you can, memorize these, okay? For a long straight wire, the magnetic field is mu0I divided by 2 pi r, where r is the distance away from the wire. The center of a loop of wire looks very similar, except it has no pi. For a current-carrying conductor, inside the conductor, if this is too hard to memorize, that's okay, but know that it's a linear function. The magnetic field increases linearly within the conductor from 0 until it gets to the surface, at which point it starts falling off as 1 over r. So that's the key thing here. Linear to the surface of the conductor, 1 over r outside the conductor. Then a solenoid outside, 0 magnetic field. Inside, it's mu0n, which is the number of coils divided by the length times current, or we replace this n over L with little n, where n is the number of coils per a certain distance.